Hello. Okay. Okay. So welcome back to DSP, and a few announcements first. Okay. So now today's the 1st of May. We have now it is May. Um, so just I was looking at our syllabus that I have been kind of adjusting the syllabus. I want to say syllabus. I've been adjusting, changing the schedule, just fine-tuning the schedule from time to time. But now it looks like we are right here, right? We're right here, May 1st. That's today. So we will continue on the topic of filter design. Is it large enough? Okay, should I enlarge it? Okay. So today is I would say the second week for filter design, or even the third week. So remember that we have talked about the bilinear transformation last time, right? So you can borrow from an analog prototype, any analog prototype, and make it digital. Make it digital through bilinear transformation. And the ending result would be an infinite impulse response filter, IIR, or IIR filter. So that is last week. But this week, I will just briefly go back to the topic of IIR design. But then today, I mainly want to introduce FIR, where F stands for finite impulse response, meaning that this filter has an impulse response that has finitely many samples. 有限多个 samples, finitely many samples. And the way we design an FIR filter, the most classic way is through the usage of a window. Okay? What does it mean to have a window? So we'll talk about that today. Okay? And next week, we will continue the filter design topic. But let me just tell you that from during the previous week and as well as today, we will use low-pass filter design as an example. Okay, so for example, last week when we introduced bilinear transformation, we talked about this Butterworth filter, which has a nice property of what? Of that its magnitude response being monotonically decreasing. That's a nice example, which is a low-pass filter. And today, again, we talk about low-pass filter. But after today, next week when we come back, I will share with you how to design high-pass. Okay? Once you know how to design low-pass, it turns out there's a simple trick to turn a low-pass filter into a high-pass filter. Okay? So let's not worry about designing high-pass for now. So today we still focus on low-pass, which is a bit boring. We talk low-pass. But I promise you that next week we talk about high-pass as well as band-pass, right? If we can design a low-pass, we can design a high-pass, then put them together, you have a band-pass, okay, which is not hard either, okay? And more interestingly, next week I would also like to touch upon a topic which is called all-pass filter. Every frequency passes equally with unity gain, with gain 1. Only the phase could be different. Okay, so there's such kind of a system, a family of such kind of systems that we call all pass. Every frequency receives the same gain. Okay, yeah. So that's the topic for next week. And then by the end of the month, we have the second midterm. So let me just remind you, friendly reminder. In this week, May 21st, May 22nd, May 22nd, we have the second midterm. And in that midterm, we'll cover all the content till here, till 2 weeks before the exam, okay? So the second midterm will be from where we were left with, maybe from here, yeah. I think in the first midterm, we cover this material, right? So the second midterm will be from April 10th to maybe May to this week, okay? So just as a reminder, please refer to this page from time to time. Okay, I'll just keep making sure that we agree on the schedule and what to cover in every exam. Right? Okay. So with that, any question? Any question from the from streaming? Okay. Okay. Yeah. So that's about the schedule. And all right, so let me now let's switch to our handout. And by the way, I have also posted the pre-note not only for today's lecture but also next week's lecture. So I just loaded 2 pre-notes yesterday. So please check it out. So today we'll be on lecture 9. Okay, today we will be on lecture 9 right here, and next week that's lecture 10. So yeah, both of them have been posted to EE class. But before we just dig into lecture 9, let's go back to lecture 8, which is IRR design. Okay, IR design. So what do we have? So last week we introduced the bilinear transformation. Bilinear transformation, and it goes this way. Suppose that we have an analog prototype, analog system function, which we want to make into to make it into digital. And the way we do that is to make a substitution. Wherever we see the variable s in the Laplace transform s, whenever we see s, we make this substitution. We force s to equal to we think of s as a function of z. So from z to s, from s to z is a bidirectional mapping, okay, a bilinear transformation. So this is to express s in terms of z. So when we replace s with this function, then we obtain. What we obtain is a function of z inverse instead. Okay, and we know how to organize it so that it becomes clear that, of course, there is a difference equation corresponding to this system function as a function of z. Okay, we know how to do that. So, yeah, as we see that in a familiar way, h of z is expressed as the ratio of b of z divided by a of z, where b and a are both polynomials. Yeah, 多项式啊. So we can find out the zero location, find out the pole location, and we know that we can construct a difference equation just with some simple algebra, just simply organizing your terms, and you obtain a difference equation that we can run on your computer. But now the question is, when we look at the h of z, it might not be so easy to kind of mentally see what the frequency response will be like. Okay, just merely by only looking at this expression, it might be hard. So therefore, we had to study some properties of the bilinear transformation. Right? We studied property that, for example, the imaginary axis, right? So the imaginary axis in the S domain, right? As you go upward from bottom up, going along the imaginary axis in the S domain, that's like doing this. If you go up in this direction in the S plane, right on the imaginary axis, it turns out that the bilinear transformation maps that axis to the unit circle in the Z domain. Okay? Imaginary axis is mapped to the unit circle in the Z domain in this counterclockwise direction. Also, because this is an analytic function, and geometrically, the transformation is conformal, a conformal mapping. Okay? The transformation is a conformal mapping, which keeps the left-hand side of your path. Keep the left-hand side to the left-hand side. Okay. So once you are going up in this direction, your left-hand side would be this half plane on the left. Right. But imagine that we are going now along this path. Then what is the left-hand side? The left-hand side, it is the inside of a unit circle. So just by the basic property of conformal mapping, we know that the transformation also maps the left-hand side, your left-hand side, okay, the left-hand side of the S-plane to the inside of the unit circle in the Z-plane. And that's a really important and nice property because, because that means bilinear transformation preserves stability. If you start with a stable system in the S domain, which means that all the poles need to be located on the left-hand side of the imaginary axis with negative real part. Yeah, okay. So stability is a sufficient and necessary condition that the system, in that continuous time system, analog system, all the poles need to be on the left-hand side of the plane. But now, after the transformation, they all go inside the unit circle, which is also a guarantee for stability. So we know that this bilinear transformation is pretty nice. It's pretty safe. It's safe to use it. If you begin with a stable system, you don't need to worry that the end result will become a non-stable, unstable system. That will not happen. Okay, so we don't need to worry about that. And then, in terms of the mapping from on the imaginary axis to the unit circle, we know that the imaginary axis has a meaning. In the S-plane, it's j times the frequency. S equals to j big omega being the frequency in radian per second, really. Yeah, 2 pi times hertz, 2 pi times the frequency. Yeah, the angular frequency. Yeah, now we have a one-to-one mapping between the entire line to the unit circle, which has a finite length of 2 pi. 2 pi, yeah, 2 pi, yeah. And there is a formula that we derived last time, which is this, yeah. The bilinear transformation sort of compress the entire frequency axis for analog into 2 pi in digital. And the formula, this equation is can be written as in terms of arctangent. Okay? 2 times arctangent big omega divided by this factor. Okay? And this factor 2 over TD is a factor that shows up in your bilinear transformation. Now there's a kind of free parameter TD that we can choose. Okay, yeah. Okay, so that's where we're at last time. So last time I didn't have enough. We ran out of time to introduce a geometric interpretation of this equation. Okay. I would like to invite you to take a look at this equation and have a kind of appreciation. How do we pack? How do we compress the entire infinitely long line into 2 pi? Right? So last time I said that you can please imagine that there is this triangle, right? There is this triangle, okay? And then this theta is then this side would wait. What I'm trying to say. So that's how I asked you to imagine there's this triangle, okay? And with j omega being the length here, with omega being the length here, and the diameter, 直径, the diameter right here, if we imagine that its length is 2 divided by TD, okay? So at least for the x-axis and y-axis, both of them have the unit of basically 1 over time, okay? The unit of frequency. So that when we imagine this triangle, then the theta right here is, you can see that theta, of course, is arctangent of 对边除以邻边, the side on the opposite, basically, you know, y divided by x. Theta, of course, is arctangent of omega divided by 2d. Okay, so that's theta. But now we know that in this formula, when we look at this formula, omega really is 2 times theta. 2 times theta, okay? Yeah. So what is 2 times theta? 2 times theta is this angle. That's omega. And I found this to be pretty simple and beautiful, so I want to share with you. This is junior high school math, right? This angle omega is 2 times theta. Why? Because we have an equal, how do you say? Because this is the radius, this is the radius, right? They are equal. And we have a triangle with 2 equal sides, right? 等腰三角形了啊。We have a triangle with 2 equal sides, and so this angle is also theta. So therefore, omega is theta plus theta, which is 2 theta. Okay. So this is a kind of a nice geometric interpretation that tells you that, indeed, for every omega, you can simply connect omega just with a straight line to this point right here on the S-plane, and then this line would intersect with a circle, with the circle right somewhere, okay? And with the circle somewhere now, if this, imagine that this is the center of your circle, okay? Then this is our angle omega. So omega this is a geometric interpretation, okay? This is how we map the entire line, at least the upper half of this line to the circle, okay? As big omega increases, small omega also increases, and the relation is that of an arctangent. Right? So this is some little sharing, but now I want to conclude this lecture by talking a little bit about the design flow, okay? Design flow. Remember that this, from now on, we will talk a lot about design, okay? Design. So usually when we talk about design in digital signal processing, there must be some sort of specification, specs. That is like a list of criteria that your design want to satisfy, okay? Specification, specs, 规格啦，开规格啊。So as an engineer, we need to do our best to meet the specs, right? 这些的规格啊。So taking again for the low-pass filter as an example, your spec, what parameters might be included in your spec, in the spec that we are given, right? So the spec might include, first, most basic is the corner frequency, right? The corner frequency. For example, corner frequency where C stands for corner. Or if you will, cutoff. Both happen to start with the letter C, okay? So the corner frequency. So we might be told that, hey, I want a filter with a corner frequency of pi divided by 10. So that means 1/10 of the Nyquist frequency, okay? If your Nyquist frequency is 8 kilohertz, hey, can you give me a low-pass filter which has a corner frequency of 800 hertz? Which might be a scenario that we might encounter, right? So let's say your client. So let's say your client might be yourself. You know, you're designing a filter for yourself, right? Yeah. So the spec may be realistically could be any frequency, okay? And in this case, you're given the corner frequency to be equal to pi divided by 10. Okay, so the thinking flow really goes the opposite direction. Opposite to what? Really, design has a thinking flow that goes opposite to analysis. Now, let me repeat this, okay? Design is in the opposite direction of analysis, right? In analysis, 做分析的时候, in analysis, when we analyze something, you are given the system, the result of design, then you try to figure out what's the performance. That's analysis. So we are all very good at that, okay? Yeah, so we all are good at that. Given the system, we can analyze the performance, okay? But design is the opposite thinking direction. You're given kind of the criterion we want to meet, but then you need to come up with a system. Okay, so here is the example. We are given the criterion we want to meet. We want to have a filter of this cutoff frequency, okay, which is given to us as a specification, right? So in the design flow, we need to find the parameters. You know? So now the flow, the second step in here is to find a parameter TD, and then use this equation to figure out the corresponding corner frequency in the analog. Okay, so here again, using the same letter C to denote corner. So for small omega c, we want to now calculate big omega c with a free parameter right here. Let me put a remark here. It turned out that this free parameter is not important. Okay, I can promise you. It turns out that TD is not important. You can just choose any time, okay? Be it 1 second, 1 microsecond, 1 millisecond, or 2 days. Doesn't really matter. 100 years, Turns out that it doesn't matter, okay? But anyway, wisely choose a TD that sounds cool, okay? Let's say 1 microsecond, okay, which sounds cool, But then we have, what do we have? Then you have this, You have this omega c right here, okay? And it turns out that what is important is the product of omega c times TD, okay? Turns out that this is what is important, okay? And you will see it in this homework, okay? In homework number 4, I asked you to design, to follow this flow and design a Butterworth filter. Design a digital Butterworth filter by borrowing its prototype in analog, okay? So you follow this procedure step by step, okay? It turns out that this is in homework 4, hopefully you will realize that, hey, indeed, what is important is the product of omega c times TD, which is this factor, okay? And homework 4, let me just give you a preview. It has the kind of manual part for calculation, 用手写的啊, handwritten part, and it also has a computer part. And you are asked to do both, okay? You're asked to use a manual calculation as well as computer library in MATLAB to perform your design of a Butterworth low-pass filter, okay? So there will be manual calculation versus computer. So hopefully in both ways you'll realize that, yes, we can achieve a design. So now after going back to, after figuring out omega c, then this is where we start considering, just under my suggestion that you can draw a circle of with a radius of omega c in the S domain. In the S domain, remember this is S domain, this is not a unit circle, okay? This is already in the S domain. And then in this homework, as you can just find out a detailed description of how to locate your poles on this circle with radius omega c, big omega c, okay? So Butterworth filter involved kind of like cutting pizza, just equally place. For example, if n equals to 6, then we equally placed 6 poles. Now that's the order of your filter. You equally place them on a circle in the S domain, and then write down your analog prototype. And then your design, and finish your design by this bilinear transformation, through this bilinear transformation, okay? So that's your design flow. Okay, so first we begin with a spec, right? Yeah. Okay, so anyway, so this design process will repeat. Okay, so in this case, you are only given the spec of corner frequency. Okay, corner frequency. But you know that somehow there is a parameter of order, that is the order. You still need to decide what's your order of this filter. Okay, what's the order of your filter? Is 6 enough? Right? Is 6 enough? So sometimes, also as a preview to this homework, sometimes we are also given another spec, okay, another parameters. So sometimes we are not only given the corner frequency, which is pi divided by 10 right here, but also the transition width. Yeah. How fast do we want the response to drop from pass band to stop band? Okay. Sometimes we are also given the transition width. So let's say we want the response, just roughly speaking, to drop from the corner frequency to below 0.01. Let's call it delta, okay? Let's say we want the response to drop from the corner frequency. Oh, wait. Corner is right here. I'm sorry. It's bad drawing. No, maybe. Let me erase this, okay? Let me erase this because corner needs to be right there. Yeah. Okay. This is your corner frequency, pi divided by 10, where the response, the corner frequency has a magnitude response of 1 divided by square root of 2. Okay, we have seen that. Yeah. So in Butterworth's design, at least, sometimes you're also given the kind of the transition. Okay, how fast we want this magnitude response to drop from 1 divided by square root of 2 to 0.01. Okay, if we call this delta omega. So let's say this delta omega there might be a criterion that you want to meet this specification of a delta omega narrower than, I'll give you a number, narrower than, let's say, pi divided by 50. Okay? Yeah, so that could be a criterion. Okay? That could be a criterion to satisfy. That could be a part of the specs. Right? So to also meet that spec, then we need to generally need to increase the order, right? Because we know that when we increase the order, of the filter, when we increase the order of filter, we can make it drop faster. We can make it drop faster and faster and faster. Okay. This is by increasing n. We expect omega we expect that we will be able to make omega, the transition narrower. It's kind of a faster transition from pass band to stop band. So this is a desired property. Okay? So nothing is for free. If you want to perform a better performance in one aspect, you might need to sacrifice another aspect. 因为大家太快，我等你们一下啊。Okay, so I was trying to share with you this very general idea. Okay, trade-off. Design. Whenever there is a design, there is a trade-off. So in this case, you'll see repeatedly, not only for IRR but also for FIR. We'll see repeatedly that if you want a narrower transition, usually you end up you need to buy that using by a heavier computation load. Increasing the order of the filter means that in your difference equation, right, there will be more terms that you need to sum up. Yeah. k equals to 1 to the order, right? Yeah. There will be more terms that has to be summed up for calculating every one sample, okay? So we trade it off, and also there will be 0. Yeah. You know that there will be also the b part, where k is from 0 to big M, okay? Yeah. So the trade-off happens here. When we want a faster and narrower transition width, we just you can earn it only by willing to increase the computation load. Okay, sometimes it's worth it, sometimes it is not. And we will see this repeatedly, not only for IR design but also for FIR. This kind of theme, this situation will keep coming back. Okay, yeah. But here we always see a trade-off. So far so good. Are you? Yeah. Any comment here? Any question? Okay, Ma. Yeah. How many people are viewing this right now? I'm curious. Huh? 11. Oh, you're eager. So for those of you that are online, if you have a question, please feel free to ask through YouTube, right? Is this currently being streamed on YouTube? Okay, now let's try that. Okay, any question on right here in the classroom? Anyway, tomorrow we have a discussion session, so we'll work out. Are you about to raise a question? No. Okay. 一样 Okay, so the question, is, will we really obtain a frequency response that looks the same in the Z domain as well as in the S domain, right? Yeah. They will. Yeah. So will they look similar? Okay. Yeah. So that's a good question. So let's go back to here. Yeah, this is my answer right here. This is my answer right here. Okay. If you're, let me try to draw a few pictures right here. So let me just intentionally, 我故意intentionally just change the x and y axis in the S-plane, okay, in the big omega domain. So here, if you have a low-pass filter, which has this magnitude response, and now this is your omega, okay? So let me just intentionally draw a picture like that. Just switching the role between x-axis and y-axis. And now we draw a magnitude response, okay? So for a low-pass filter, for the Butterworth filter, we have a corner frequency big omega c right here in your prototype. In your prototype, and we know that the response is going to drop from 1 to 1 divided by square root of 2, okay, right here. And then it's just monotonically decreasing, but never touches 0, okay? That's a low pass. That's how a low pass Butterworth filter looks like in the big omega domain, in big omega, okay? And of course, but after bilinear transformation, since we know that every frequency big omega is mapped to a small omega, therefore, your frequency response right here, that's a magnitude response, will be, you just find the one-to-one correspondence, okay? 一个 one-to-one 的一个关系啊. You just find the one-to-one correspondence between big omega and see how it maps to small omega. And here we have that formula, right? Small omega is equal to what? 好像是这样子，是不是? Is it this? Yeah. Yeah. That's an expression. That's a geometric interpretation I was talking about. Okay? Use this, and then. So really, what this relation means that is every omega here, we know it maps to a small omega somewhere. Okay, so big omega c here map to a small omega c right here, and so on. And this relation, so if we go for bigger omega c, now the gain is smaller. So bigger omega right here, you go to a higher omega right here, okay? And the gain is smaller. And when we further increase omega, the small omega also increases, but then it approaches the highest frequency is pi. Okay, so this is how you, the result of your design should be a attenuation from 1 to 1 over square root of 2 right at small omega c, where small omega c will be equal to 2 times tangent big omega c td divided by 2, because that's how we started our design. Yeah, please make sure you understand this. Okay, and then when frequency further increases, the response eventually drops, and then it touches 0 right at the Nyquist frequency. It touches 0 right there. So of course, the frequency response in analog can extend indefinitely, for all frequency. But in kind of after we go to digital, small omega has a range from 0 to pi. Okay. So the answer, my answer to your question, will they look similar? Yes, they will look similar. And of course, let's say if you have to design an analog filter which looks like this, okay, then your digital filter, sure, after bilinear transformation, will also have a similar shape. They will have a similar shape. The way the gain goes up and down, but also phase, frequency response goes up and down with changing phase. That kind of sequence, that order will be preserved when we migrate from analog to digital. 那个顺序, that order, that trend, that shape will be similar. I hope that answers your question. 谢谢. So anyway, tomorrow we discuss the homework. Please take a look if you have time. It will be about Butterworth filter design. Okay. Now, with that, so shall we now move on to my next lecture? Okay. Let's move on to the next lecture number 9, which is about FIR design. FIR design using Windows. Okay. FIR design using Windows. And this is an old handout from 7 years ago. I apologize, nothing much has been added. Same handout, and it was for grad school. So you guys, I tend to teach exactly the same materials, either for this course or for the grad school. Anyway, FIR filter design using Windows, where FIR, let me just repeat, stands for finite impulse response. Okay, that means that your H of n, the result of your design, that impulse response will be non-zero only for finitely many samples. The response will not last forever. Okay, finite impulse response. That's what it means. Okay, now so a bit about kind of terminology, right? So as I suggested that still today we are going to talk about low-pass filtering. Okay, so there are a few terminologies that we need to agree upon. So here we have 3 words. Okay. We have 3 words, and this picture is called a tolerance scheme. 忍耐的忍受、承受、容忍tolerance. A tolerance scheme. Okay, so here we have the passband, and it should be pretty clear. Passband is where we allow the frequencies to be preserved, okay, to show up in your output. Passband, that component will pass, and in contrast, the stop band is where we receive. The system should demonstrate small gain. The system your system should produce small gain. Here, the y-axis is the magnitude of your frequency response. Okay, the magnitude response right there, and the frequency goes from 0 to pi. Okay, but then passband, in between passband and stop band, please remember that there is the transition. Sometimes we also call it transition band. Okay, in between passband and stop band, there is a region. There is a region that sort of serves as a buffer, 一个缓冲区, as a buffer where we allow the magnitude to drop sort of gracefully, 优雅的, elegantly, gracefully from passband to stop band. So yeah, so there is a kind of a, in your specification, usually we talk about transition. Okay, transition is a requirement. Ideally, we want the transition to be narrow. Okay, so ideally, transition should be narrow. Desired to be narrow. Okay, we want the transition to be narrow, but very soon you'll find out that it cannot be 0. There's always a kind of a frequency width that we need to, a space that we need to, that is required between passband and stop band. The transition is never ideal like an ideal low-pass filter. Okay, ideal low-pass filter. So just in contrast, when we talk about ideal low-pass filter, the transition is infinitely sharp. Okay, passband, 直接, directly stop band. That's ideal filter. In ideal low-pass filter, then the transition, if we just vaguely call this delta omega, okay, just roughly. In ideal filter, delta omega is 0, and that's why we call it ideal. Okay, ideal filter is like that, but very soon we'll discuss why this is impossible to implement. Okay, it's conceptually it's there, yeah, but it turns out that it is impossible to implement. So therefore, for any practical design, there's always a finite transition, non-zero transition. Okay, but still we desire it to be narrow. Okay, we still desire it to be narrow. Yeah. Okay, so in this tolerance scheme, we have passband, stop band, and in between we have the transition. So these are the terminologies that we want to agree upon. But also then we have a few additional parameters. You know? For example, the transition happens between the edge of passband and the edge of stop band. So here, these two frequencies are called the edge frequencies. Edge, 边缘的, edge frequencies. These two frequencies, omega, edge of the passband, edge of the stop band, denoted as omega p, omega s, right? And also we have a few parameters that we will that uses the Greek letter of small delta. Okay, small delta. So that means sort of that's the tolerance we're talking about. Okay, ideally we want to design a filter that has unity constant gain for passband and 0 gain for stop band. Okay. But in practice, what we end up with is usually your FIR filter usually contains ripples, 涟漪 ripples 叫 in Chinese 就是波动产生的涟漪叫做 ripples ripples So the response at passband inside the passband will never be ideal as a constant one. It never will happen. Okay, that will never happen. FI or IR. Okay, so you need to kind of tolerate some deviation from small deviation from your ideal gain of one. Okay, so let's say we can tolerate our passband gain 1 plus, yeah, we say that we can tolerate our passband gain h of ej omega, the passband gain to be in between 1 minus a small delta and 1 plus a small delta, okay, another delta. As long as it falls in between this small range, we are happy, okay? So that's also a kind of some parameters in your specifications. Sometimes we are just given that, hey, the passband ripple should be not too large so that the gain is maintained in between 1 minus a small delta and 1 plus another small delta. Okay, so these are called the passband ripples. The passband ripples. And similarly, for the stopband, ideally we want the gain to be completely zero. Okay, we want any frequency there to be completely rejected. But in the end, it's never possible, right? So now we can talk about spec, okay? So you might be given a spec that, hey, we want the stopband gain to be smaller than this. We want the passband to be suppressed by at least so much. We want the passband gain. I mean, this is for the did I say passband? Yeah, anyway, let me finish writing right here. The passband gain should be close to 1 when omega is smaller than omega p, okay? Or maybe with an equal sign, doesn't really matter. And the stop band here is we can have a tolerance that stop band gain itself needs to be smaller than a stop band tolerance for any omega that's greater than omega s. Okay. So these are like just a kind of a picture that tells us a lot about some general designing goals for low-pass design. Okay, for designing a low-pass filter, we talk about transition and we talk about ripples. And ideally, let's summarize. Okay, ideally we want the ripples to be small and the transition to be narrow. Okay, so with that, let's maybe take a 10-minute break. When we come back, we talk about how to start designing the FIR filter. Right. No. Okay. No. Hello? Okay, yes. So let's continue our journey in filter design. FIR, finite impulse response. So we've discussed some terminologies, passband, stopband, transition, tolerance scheme, and so on, okay? So now, what's the idea of using, we say using windows, okay? So the idea is that, as you very soon see that when we have an ideal low-pass filter, we can go back to the time domain, right? So using inverse Fourier transform, we see that the inverse transform is a sinc function, right? But the sinc function is like extends, 它延伸啊, extends infinitely in both directions of time, right? It extends to infinite in for negative n and also positive n, okay? So can we implement that, okay? I don't think you can do it, okay? Unless we're talking about imaging, okay? Image has a finite size. Maybe you can, if this is some space domain, spatial frequency, then maybe there's a way, okay? But when we talk about time domain signals, time has a direction, okay? You never go back in time, right? So let alone going back indefinitely, okay? So now the idea of window is somehow we need to truncate, to make a truncation. 要截断它啊, you need to just terminate this response somewhere. Okay, let's say we terminate right here, and symmetrically we also terminate right there. Big M, negative M. Okay, then we also only keep this middle part. Okay, this middle part, however long it is, it has finitely many samples. So it's a long filter, but not infinitely long. It has a length of 2n plus 1. Then we claim that this is a design. Okay, all the design looks straightforward. Okay, once you know it. Okay, just looking at this sinc function, and then keep the middle part symmetrically. Keep the middle 2n plus 1 points. Then you get an FIR filter. It's as simple as that. Okay, and this is something that. In principle, you can implement. Okay, you can implement because it has finitely many samples. So that's the idea. So window, in a sense, means that we need to just confine our interest, focus on the middle part, using some sort of. In this case, we say that the sinc function has been windowed verb. Okay, it has been windowed by a rectangular function, or we use the rectangular window to process the impulse response. Okay, so that's the idea. So with that, let me just we are ready to go into some details. Okay, so that's the passband, transition, stopband, tolerance schemes. So here is the idea. In this way of designing filter, we begin with the ideal low-pass filter. This is where we begin. We begin with the ideal low-pass filter with this desired response. Okay, where this D stands for desired. A desired 我们想要的desired response of that being 1 in the passband and 0 otherwise. There's no transition. Ideally, the ideal filter does not have any transition. Okay. And also to make a sketch of the frequency response, it's 1 in the passband and 0 in the stopband. Okay, stopband is from cutoff frequency to pi. Okay, simple enough. So we know that with this desired response, we can apply inverse DTFT. We can apply the inverse of DTFT. So let's recall the formula, right? So do we still remember the inverse DTFT? It's 1 over 2 pi, right? 1 over 2 pi and integral something. Integral h e j omega, what? E to the j omega n d omega, right? We have done it a few times. We know the result is the sinc function. The result of the sinc function for non-zero n. Okay, we need to be careful that this sinc function now cannot be evaluated when n is 0, strictly speaking. 严格来讲, strictly speaking, this cannot be evaluated at n equals to 0. So therefore, we know that n equals to 0, it approaches this value. Okay, it approaches this value, so we have the corresponding impulse response, so to speak, has, it's like that. The impulse response is looks like that. Impulse response look like that. Okay, it looks like that, and if you will, you can even figure out the zero crossing here. Okay, it might be kind of nice to know that. Where is the zero crossing? This zero crossing is near, should be near n equals to pi divided by omega c. Okay, where omega c is the cutoff frequency of your ideal filter. Okay, near. I said near because this number might not necessarily be an integer. Okay, okay. So there are a few problems right here. There are a few problems. First, this impulse response is non-causal. Right? It's non-causal. Ideal filter is non-causal. Ideal low-pass filter is not causal because it has some non-zero samples before time 0. Right? Because some samples at n before time 0 might not be, there are a lot of them being non-zero. Most of them are non-zero, okay? And secondly, so the main problem. The main problem is that the response is infinitely long on both sides. On both sides. So when you use it, you can imagine that if you want to use it, how do you calculate the convolution? That's the problem. That's a problem. When we use a filter, we need to somehow be able to compute its convolution of the impulse response with your input signal, right? But then with this infinitely long filter on both sides, and I think the main problem is that this cannot be expressed as cannot be expressed as a difference equation. I think that's actually the main problem. Cannot be I'm trying to find the verb. I'm trying to say that we cannot replace this with an equivalent difference equation. Okay, there's no equivalent difference equation, and we can argue that. Let me say this impulse response cannot be made equivalent to the impulse response of a difference equation. Okay, turns out that cannot be achieved. So this is a rather long remark I'm making right here. I think that's the main problem. Anyway, so I'm trying to convince you that this cannot be implemented using a difference equation. This exact solution, the sinc function. Okay. So here is a kind of an alternative. We need to somehow work around. We need to have a design. So let me suggest that this is our design. Okay. the idea is to keep the middle part. This is a design philosophy, if you will. Let's keep the middle part. Keep the middle 2n plus 1 samples. Okay? So let's define our filter as being equal to the ideal impulse response at the sinc function. For the middle, for the 2n plus 1 samples around time 0, keep them. I suggest here, let's try this. Okay, this is a design. Yeah. And then truncate, make the truncation. Set the impulse response to be 0 outside. Okay, outside this region. Outside this region. So for example, let's count. If big N is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, let's say big N is 11. So we will keep the samples from minus 11 to plus 11. Okay, let's count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Forgive me, but you know what I mean. The response should be, should be symmetric. Okay, let's say we keep the time between plus 11 and minus 11, and only keeping the middle part. We're going to call this our design. Okay, by keeping only the middle part. So let's say this is our design. We keep these samples. This is our design. So please bear with me if my drawing is not accurate, but you know what I mean. Keep the middle part, which should be symmetric. Okay, and then elsewhere, let's say all zeros, I'm going to ignore. I'm going to be just abandon. I'm going to just omit. I'm going to just exclude all the other samples by only keeping the middle part. Only keeping the middle part. Okay, keeping these part while excluding the other part. So that's our design. And I claim to you that this is already a design. Okay, and we'll analyze the frequency response after of this design. Okay, but then after we note that I forgot what I'm trying to say. Note that what? Usually I bring my cheat sheet. Yeah, I print out my lecture from previous years, but today I forgot to bring them. Unfortunately, I know the content well, but I forgot what I was trying to say here. Note that. In other words, yeah. But I'm trying to say that note that the action of keeping the middle part is equivalent to multiplication. We are multiplying our sinc function with the rectangular function. That's what I'm trying to say. That might be what I was trying to say. Okay? So, yeah, keeping the middle part while excluding the whatever that's left outside means that we are going to introduce a window function here. So let me try. Let's know that truncation is equivalent to multiplying with the rectangular function. So to be more precisely speaking, we should introduce this W of n. Okay. More precisely speaking, let us introduce the window function. The rectangular window, we mean this function. This is a function. Okay. This function is 1 in between minus n and n, and 0 elsewhere. And it is 0 elsewhere. Okay. So therefore, what I just suggested is to multiply our desired function by the window function. They multiply in the time domain, sample by sample. We are performing, so here, just another way to say this, By keeping the middle part, we mean we multiply the sinc function sample by sample with this rectangular window that we just introduced. Okay? This function is called the rectangular window. It's called the rectangular window, 矩形的 rectangular window. And our design, so I'm introducing to you, I'm suggesting to you that our design involves multiplying the desired response with the window function. And the advantage is that after multiplication, the length suddenly becomes finite. Yeah, because we just abandon everything that's outside, right? So now by concentrating on the middle part, this becomes a finite impulse response. And further, because we have multiplication in one domain, what do we have in the other domain? Multiplication in time domain means convolution in the frequency domain. Okay? So effectively, the design, after our design, by simply keeping the middle part, this design leads to a frequency response that can be expressed as a convolution of the desired response with the Fourier transform of the window function. Let me say this again, because this is important. Okay? Multiplying in the time domain means in the frequency domain, the resulting frequency response is not going to be ideal anymore. But it has a close relation to the ideal filter. Okay? The ideal response still is this. Yeah. Now we are going to do a convolution. Here, theta is just a dummy variable, but it's really the frequency. Okay? Now we're going to just convolve the ideal magnitude, the frequency response, with the Fourier transform of this window function. And in general, the window function can be something else. So let me just promise you, we'll talk about some other kind of windows. Not just a rectangular window, but in this case, when we begin, let's suggest we use the rectangular window. Okay? And the result would be a frequency response that deviates from ideal in terms of by convolution. The response will be the convolution of ideal response with the Fourier transform of the window in the frequency domain. That clear? Or you can write, the convolution in the frequency domain sometimes is denoted by this operator with a star and a circle to emphasize that this is what we call a cyclic convolution. Cyclic. Cyclic convolution. 循环式的cyclic convolution. Okay, so that's step one. Strictly speaking, we have two steps. The first step is just to keep the middle part. And we know that the result will give us a frequency response that is not ideal. But then next we talk about how, before we talk about how, in what ways the response deviates from our ideal response, before we do that, let me tell you that there actually is a second step. Rigorously speaking, the first step is to keep the middle part. But the problem is, strictly speaking, even after keeping the middle part, is the filter causal yet? Even after keeping the middle part, the filter is still not causal yet, because the left-hand side, the half of the samples are still before time zero. The later half, the second half is after time zero, and there's a middle sample, right? But there's another half of all the samples which occur at the negative time. Okay, so strictly speaking, this filter still is non-causal, and we hate it. Okay, we hate anything. Please hate non-causal systems. Okay, so we hate it. So strictly speaking, we need to shift everything to the right to make the system officially causal. Okay, turns out that in the end, we often don't need to worry too much about this second step. But in fact, we need to, for the sake of being rigorous, we need to say step 2, Hn is the result of shifting the first step to the right by n samples, so as to make it shifting to the right to make the filter rigorously causal, a causal filter. Okay. Is that clear? So that so keep in mind. So this is really change. The idea is to shift everything to the right by 11 samples. When after shifting everything right by 11 samples, or equivalently, you can think of that now we have a new time zero. Okay. Now this is time 0, time 1, time 2, time 11, and the end. The last non-zero sample right here becomes time 20. Is it 20? 22, I think. Okay. The time range was -11 to +11, but after shifting the time becomes from 0 to 22. That's where our impulse response can be non-zero, and it's a finite impulse response. We have finitely many samples of non-zero. Finitely many non-zero samples. Okay. Right. So, and a bit of a comment right here. So after this step, we know that what happens in the frequency domain, if I ask you. When we shift the impulse response to the right, we delay it by n samples, right? So what happens in the frequency domain? We know that it's going to introduce a linear phase term, okay? So strictly speaking, now our design h of ej omega is equal to h times the ej omega times e to the j big omega n, and there should be a negative sign, okay? So the resulting filters is just a shift, to make it rigorous, so that we can talk about implementation, right? We can talk about implementation to make it causal. Okay, so with that, now next I want to introduce to you what's going to happen when we convolve the ideal filter response with the Fourier transform of the window. Okay, So in the next slide, we are looking at two things. Here, for the first curve right here, we see this is frequency domain. Okay, this is frequency domain with a dummy variable theta. Okay, this is frequency domain, and we see the ideal response right here, having unity gain in the pass band, and zero gain for the stop band. But now, please try to imagine how do we convolve this ideal low-pass magnitude with the Fourier transform of our window. Okay, the Fourier transform of our window. So this becomes tricky. Okay, because our window is rectangular, so it looks like rectangle in the time domain, but in the frequency domain, it looks like sink. But here we are convolving it with a frequency response which looks rectangle in the frequency domain, and we have shown that in the time domain that looks like sink. So things could be a bit confusing. Please sort it out when you go home. Okay, But anyway, so now here what we're seeing here, this curve right here is the Fourier transform of our window function. Anyway, so now next, I ask you to imagine with me. Let's work out what will happen when we, let me just maybe enlarge how do I enlarge it? I want to make it larger. I want to make my line thicker. How do we do that? This is getting stupid. Forget all this. 有时候软体改版以后不会用啊。So here, let me just draw. So this is, roughly speaking, is our Fourier transform of the rectangular window. Okay, before shifting though, yeah, before shifting the time. Okay, so now everything's real here. Oh, by the way, everything here in the frequency domain is real. That's why we can see negative magnitude. Okay, believe me, because now we are still symmetric in time domain, so everything's real here. So let me just add note here. Here, the Fourier transform of W is real, and our ideal response is also real at any given frequency. So now let's work out together how do we calculate convolution. Okay, so convolution means that we are what? We are going to shift one of them, flip and shift one of them, right? And in this case, we imagine that the desired response is fixed, while we are going to flip the Fourier transform of our window. We flip the purple part. We flip it, but it turns out that when you flip it, it's still the same shape because it's symmetric. Okay, yeah. But we flip it and shift it to omega, frequency omega, right? So that's the result of flipping and shifting our Fourier transform of the window to center around frequency omega. Okay, and then what do? Then we multiply and calculate the area under the curve, right? Yeah. So we calculate area under the curve, right? So for every omega, we can just calculate the area. And we know that positive and negative part will cancel. So we calculate the area in between these two frequencies. Why? Because elsewhere is 0 for the ideal response. Okay, so we calculate really the overlapping area under the curve right here. That's how you calculate at every omega. Okay, and later we are going to shift. And later we are going to shift this to the right, by a little bit. You see what I mean? And then calculate the area under the curve after shifting it to a new omega. But then the calculation ends right here. Because now, when we keep shifting to the right, now the main lobe of the Fourier transform, this is the main lobe. Now the main lobe falls outside the passband. So the overlapping area becomes small. Once we shift the main lobe, this is the main lobe. Once we shift the main lobe to the right, further to the right to become outside, when they don't overlap with the ideal response, the result of calculating the area becomes small. So that's the idea. So now, can you imagine shifting now in your head, shifting this thing to the left and to the right and calculating the area? Then this is what you get. Then this is what you get. So I ask you to make imagine this in your head. Can we agree on that? This is convolution in action. Okay, shifting that purple thing to the right to the left, and it has a main lobe, right? So when the main lobe significantly overlap with the passband, we see a high response. Okay, there will be ripple because this thing has ripples there. So it will not be a constant, but then it will be large. But until now, when since I love doing this, wait. Now, when the main lobe overlap with the passband, and this is our omega right here. This is our omega for now. The gain can be high. Okay, but now when the main lobe starts moving out and have a little and more smaller and smaller overlap with the passband, the gain, the result of convolution is going to decrease. And the entire thing should be what? Oddly symmetric around the edge of the passband. Okay? It's moving out, right? So we have the opposite thing is happening. We're having ripple in the stop band. Ripple in the passband, ripple in the stop. They look symmetric. This here, we should have some sort of asymmetry. Yeah, asymmetry, meaning that, yeah, two kinds of symmetry, or even symmetry, asymmetry, okay? Asymmetry around at the edge of passband. And this is the result of our design, okay? Our design is gonna end up with a frequency response from 0 to the edge of passband and to Nyquist. And this frequency response, somehow this is a copy from the textbook, okay? Somehow we already know that the response is always going to have a period of 2 pi, okay? This response is going to always repeat it every 2 pi, yeah. Okay, so is this okay? Yeah. Convolution is actually convolution in the frequency domain, okay? When we convolve our ideal response, with the Fourier transform of that window, okay? This is what we get, okay? Yeah, so next, a few more words about the Fourier transform of this window, okay? The Fourier transform of this window, remember that our window is the rectangular window, right? So W of n is, in this case, in the textbook, it talk about after shifting, okay? So after shifting, the notation in the textbook goes that we have a total of n plus 1 samples. That's for the textbook, okay? So this is already after shifting. After shifting both our ideal response and the window to the right. So they begin with time 0, okay? So they begin with time 0. So it turns out that you can calculate the Fourier transform of the window because we care about it. Okay? We care about Fourier transform of window, and that Fourier transform of the window is going to be summation W of n e to the minus j omega n, right? Here n is from 0 to n plus to m. A total of n plus 1 sample means that in the textbook, the time lasts from time 0 to time m. Okay? Time 0 to time m, a total of m samples. And here, since the rectangular window is just 1, I mean, let me put infinity here, but because W is all 1 for the rectangular window, so now we sum from 0 to big M, e to the minus j omega n. Outside, we don't care. We don't care about the outside. Outside, the window is all 0. So really, this is the result, okay? When we just mark the absolute value, then this window has the magnitude spectrum, okay? The magnitude spectrum is going to look this way. The magnitude spectrum is going to look this way, and you know that this expression, okay, this expression just peaks in the middle, and 8 is simply equal to the number of samples. Okay, 8 in this case, 8 is equal to the number of samples, the DC component of the Fourier transform of our window. Now, it's going to peak in the middle with a value of 8 right here if we have 8 samples. Okay? If the length of the window is 8, then in the middle it peaks at 8. And then it crosses 0 at what? At 2 pi divided by 8. At integer multiples of 2 pi divided by 8. Okay? So this should be 4 pi divided by 8, 6 pi divided by 8, and so on. And pi is 8 pi divided by 8. So for further discussion, for the sake of further discussion, we are going to call the middle part. I already did that. The middle part is referred to as the main lobe. The main lobe, where all the other things right here, what happens on the side they are called the side lobe. Side lobes, one side lobe, two side lobes, the main lobe. Okay, so these are our kind of terminologies we need to agree upon. Main lobe is in between this case, and the width of main lobe now will be main lobe width will be what? Will be from here to here. That's the main lobe width. That will be 4 pi divided by 8 in this case, when we have a rectangular window of length 8. Okay? Then the main lobe width, the width of that middle part in the frequency domain, the width there can be simply figured out. Okay? You can figure out that, and there are also a few extra lobes elsewhere. Okay? So maybe it will help you. The main lobe in Chinese is called, does anybody know? Main is 主要啊 ，main 主数啊 that's good. Yeah. 主数啊 what I learned is 主 lobe is 主瓣 花瓣的瓣 main lobe, and side lobe can be called side 旁 okay 旁瓣 side lobe, something that happens on the side. Okay. All right. So this is generally true. Yeah. I've pointed out that the height is equal to the length of the filter of the window, and the main lobe width is inversely proportional to the length of the window. Right? Okay, so this is an important property that I want to point out. Hopefully we will all get familiar with the idea that when the length of the window increases, let's figure out what will happen in the frequency domain. When the length of the window increases, that means the peak is going to grow, and the width of the main lobe is going down, inverse proportionally, with an inverse proportion. The width of the main lobe is inversely proportional to the length of the window in the time domain. Okay. And why does this matter? Okay. And why does it matter? I hope I have a slide somewhere. Let me jump to this slide first. Okay, jump ahead to this slide because we're kind of running out of time. Why does this matter? So to summarize today's idea, okay, today we talk about beginning with an ideal response like that, right? But then we say that this cannot be implemented. The best thing we can consider doing is to keep the middle part. But how much do we keep, right? Do we keep a lot of points, or do we keep only 3 points? Probably 3 is too little, right? But is 8 enough? Is 11 enough, right? So it turns out that we just learned when m increases, when the length of the window increases, then the height of the main lobe increases with increasing m, while the width of the main lobe decreases with increasing m. So it's growing taller and narrower when we increase m here. And increasing m means keeping more samples, keeping more of the middle samples, right? Which is usually desired. In what sense? In what sense? In that its frequency response is becoming more and more ideal, right? And that makes a lot of sense, right? By keeping more and more samples in the time domain, of course, in the frequency domain, it's going to be more and more ideal. Okay? And it also shows up in this figure. So we have talked about shifting this component to the right and to the left, right? But now I cannot shift it. No, it doesn't happen. Oh, stupid. When we talk about shifting it to the right or left, I'm making the convolution in the frequency domain, right? And the end result is a frequency response, a non-ideal frequency response with ripples in the passband, with ripples in the stopband. Because here we also have ripples in the Fourier transform of the window, okay? But the kind of most important message here is that you can always improve the performance by willing to use a larger M. Okay? By willing to use a larger M, then imagine that the width, after using a larger M, maybe we have a narrower main lobe, and which looks like that. The side lobe also follows on both sides. Narrower main lobe, but a higher height of the main lobe also. So the resulting frequency response, what do we get? You will get a resulting frequency response that has a sharper transition from passband to stopband. Sharper transition. You end up with a sharper transition. You can end up with a sharper transition, and also the ripple can be more reduced at every frequency. Okay, so that's a result of increasing M. Better performance, narrower, in terms of having a narrower transition. Okay, so the message is that by increasing M, when M increases, main lobe with delta omega also is inversely proportional. It decreases. Therefore, transition width of your filter, actually I'm not used, yeah, let me stick with the notation right here. It turns out that the main lobe width is denoted as something different, okay? It's probably denoted as using another symbol. Let me figure it out, yeah. Main lobe width, yeah, that's the main lobe width, okay? So let me stick to the notation right here. The main lobe width, delta omega sub m, decreases. And therefore, the transition width, now it is denoted as delta omega, also decreases. Geometrically speaking, okay, also decreases. And that's desired, okay? So again, before you go home, remember, increasing M leads to a better performance in terms of transition width. So again, you see an example of trading computation load to earn a better performance, right? If you need a faster transition, we need to somehow be willing to consume more power or enlarge your VLSI circuit area. Okay, yeah. So this is inevitable. Better performance, you need to sacrifice. You use more budget. Okay, use more money. Okay, money. All right. Any question right here? So that might be the end of a lecture I want to give today. So next week, when we come back, we will introduce a few more different kinds of windows. But I also want to point out one funny thing, okay? The ripple here, even though I said the ripple gets smaller at every frequency, but it turns out that the largest ripple here is something that you cannot get rid of. You cannot get rid of this largest ripple. And it's called the Gibbs phenomenon. We'll talk about that next time when we meet. Okay? But tomorrow, when we come back, please prepare for discussing the homework. Okay, with that, I'll thank you for being here. Thank you for watching the video, and see you tomorrow. Thank you.